This is video number 6 on materials. It's about strain energy or elastic potential energy. If you stretch a spring, then how much work do you do? Well, we know an equation, work equals force times distance, but if you stretch a spring, the force you need to stretch it gets bigger and bigger and bigger. So what you can say is that the work is the average force times the extension, in which case, if it's a straight line, then the average force is just half of the maximum. So it's a half Fx, and we can substitute into that a half kx squared. So, and that's an expression for the energy stored by a spring, a half kx squared. There is an argument here you should know, is that basically the work done in stretching the spring is equal to the area under the line, and the argument goes that it's actually the area of all those little rectangles added together. Each rectangle is F times delta x, so all of those F delta x's added together is the area, and that's useful if we're not talking about a straight line graph. It is still equal to the area. Have a go at this question though, a very typical question. And the answer is that 3.27 meters per second. This little calculation, kinetic energy is a half mv squared, and then so the velocity is the square root of 2ke over m. Comes up a few times on the A-level physics course. It's worth remembering. V is root 2ke over m. Yeah, as I mentioned earlier, the area under the graph is the work done stretching. Now, for your elastic potential energy, it's just the triangle, and we say that energy is recoverable. We can get that energy back. We can use it to fire a projectile or whatever. The other area, the darker area, is the work done breaking bonds. Okay, that's not recoverable. We'll not get that energy back. Okay, going back to this, you might remember me saying that material A is stronger and material B is tougher because you have to do more work to break it. And I know that because the area under the graph is bigger.